Hello, it's Stat 134, Lecture 24. This is a special lecture on the moment generating function. This is not in the book. Next time we'll cover section 4.5. So what we're doing, the moment generating function is about the kth moment of a random variable and a way to calculate the kth moment relatively easily. So the kth moment is the expectation of the kth power of x. So for example, the first moment is just the expectation of x. The second moment is the expectation of x squared, and so on. So for example, the variance is the second moment minus the first moment squared. Computing the moment of a random variable is sometimes hard because it involves computing complicated integrals or sums. But the moment generating function allows you to compute the moments by computing derivatives, which are generally easier. So as an example, let x be Bernoulli p. We know that the first and second moment of x is just p, as you can calculate directly. Let's calculate it using a moment generating function. So we'll see shortly that the moment generating function for Bernoulli p, which is a function of t, a variable, a real number, is 1 plus p times parenthesis e to the t minus 1. And if we take the first derivative of this and set t equal to 0, we easily see that we get p. If we take the second derivative, set t equal to 0, we easily see that the second derivative, we easily see that the second moment is also p. So that confirms what we calculated above. Furthermore, you can very easily see that all moments are p. But to find moments, we take derivatives of the MGF and evaluate it at t is 0. But what is the MGF? So let's recall that the expectation of a function of x is, let's say x is continuous, is the integral from minus infinity to infinity of g of x, f of x, dx. And so the moment generating function is the expectation of e to the tx. So e to the tx is g of x in this case. So if x is discrete, then we just have a sum instead of an integral. So let's derive the moment generating function if x is Bernoulli. So now we know x just takes two values, and so we can just plug in directly, and very easily we see that the moment generating function is what I claimed earlier in the boxed formula here. Now, why is the moment generating function, the kth derivative of the moment generating function, evaluated at t equals 0, the kth moment? Well, let's recall the Taylor series for e to the y. So e to the y has this Taylor series. Now, if t is in R and x is a random variable, let's let y be tx. So then e to the tx has the following Taylor series, and we can take the expectation of this. And so here I'm distributing the expectation across an infinite sum, which requires some justification, but let's not worry about that now. And we can pull the t, constant t, out of the expectation. And so, for example, if you take the first and second derivatives, set them t equal to 0 of those, you can easily see that you pick out the first and second moment. So essentially, the moment generating function has information about all of the moments, and you just need to pick it out by taking the kth derivative and setting t equal to 0. So more generally, what we do is we take the kth derivative of the moment generating function, and then we pass the derivative inside the expectation. Now that requires some justification, which involves dominated convergence theorem and some real analysis stuff. If anyone is interested in that, come talk to me and I'll provide you details. But we're not going to worry about it here. And then you'll get the kth moment. So in summary, the MGF contains info about all the moments. By taking the kth derivative and evaluating at 0, you get the kth moment. So, however, note that an MGF doesn't always exist in an interval around 0, and I provide an example of such a case at the end of these lecture notes. You care about this because of the following theorem. If an MGF exists in an interval around 0, then the kth derivative at t equals 0 is the kth moment. So we need an open interval around 0 so we can take the derivative at 0. So then we did a non-trivial example of calculating the moment generating function for a gamma. So we have the density of gamma, and we also recall the gamma function. We write out the definition of the moment generating function and pull out a constant from the integral. Now this integral will converge for t less than lambda, because you can see that that is actually the variable part of a gamma, so you know that that's going to converge. Furthermore, you know that t greater than lambda wouldn't converge, because just think about what that looks like. That's an exponential increasing, so the area under that curve is definitely not going to be finite. So we do a u substitution here in such a smart way that in the bottom here we get 1 over lambda minus t to, I guess, the rth power. We pull this outside the integral, and we beautifully get exactly the gamma function here, which cancels the gamma function in the denominator. So you end up with lambda over lambda minus t to the rth power for t less than lambda. So lambda here is positive real numbers, so this will contain an interval around 0. So now let's recall that if an MGF exists in an interval around 0, which it does in this case, then the kth derivative is the kth moment. So I asked you guys to compute the first 2 moments here, and it's just pure taking derivatives, some calculus here. So the first moment's absolutely correct, because we remember the expectation of a gamma, and the second moment, I know that's correct because the variance gives you the correct answer. If a random variable x takes values 1, 2, 3 with probabilities 1/2, 1/3, 1/6, the moment generating function just has 3 terms, and you can write out what it is, and that's for all t. And then finally, we did this for the geometric. So if x is geometric 1/3, you can calculate what the moment generating function is. Here we have an infinite sum, and I'm really going to try and do some manipulation here so that I can get rid of that infinite sum, that I can write that infinite sum as a geometric sum, which I managed to do. That geometric sum converges exactly when e to the t times 2/3 is less than 1. In other words, t is less than log 3 over 2. And you get your moment generating function as shown in the box here. Okay, I'll see you guys next time. Have a great day.